What if the stars weren't just points of light in the night sky, but destinations waiting to be explored? Faster-than-light travel, a concept that once lived only in the pages of science fiction, is now a frontier where science and imagination collide. Today, we're diving into 25 incredible theories that could make the impossible possible, unlocking the secrets of warp drives, wormholes, and cosmic shortcuts that might one day allow us to traverse the universe in the blink of an eye. These aren't just wild ideas, they're grounded in the latest scientific research and the boldest speculations from some of the brightest minds in physics. So buckle up as we take a journey through the most mind-bending concepts that could redefine not just how we travel, but how we understand the very fabric of space and time. The future of interstellar exploration starts right here. Let's go. Imagine standing on the edge of a vast ocean, knowing that beyond the horizon lies a world of untapped resources, new frontiers, and perhaps even other civilizations. Now picture that ocean as the cosmos itself, an infinite expanse of stars, planets, and possibilities. But here's the catch, even the closest star to our solar system, Proxima Centauri, is over 4 light-years away. That means with our current technology, it would take tens of thousands of years to reach it. That's longer than recorded human history. This isn't just a technical challenge, it's a barrier that limits our potential as a species. Faster-than-light travel isn't just about speed, it's about survival. Earth is a fragile oasis in a universe that can be both beautiful and hostile. From asteroid impacts to the eventual expansion of the Sun, our long-term survival depends on our ability to venture beyond our solar system. But even more than that, it's about exploration. Humans have always been driven to explore, to push boundaries, and to answer the big questions. Are we alone? What lies beyond the next star? Faster-than-light travel could give us the tools to pursue those questions in ways we can barely imagine. Beyond survival and curiosity, there's the promise of discovery. Imagine a future where we could harvest resources from distant planets, or even establish colonies in other star systems. Picture the scientific breakthroughs that could come from studying alien ecosystems or encountering intelligent life. Faster-than-light travel wouldn't just change how we explore space, it would redefine what it means to be human. It's not just a dream, it's a necessity for the next chapter of our story. And that's why breaking the light barrier isn't just a challenge for physicists and engineers, it's a challenge for all of us. Albert Einstein's theory of relativity isn't just a cornerstone of modern physics, it's a revelation that rewrote our understanding of the cosmos. At its heart lies a simple yet profound idea. The speed of light, roughly 300 million meters per second, is the ultimate speed limit in the universe. No matter how advanced our technology becomes, nothing with mass can ever reach or exceed this cosmic speed limit. This isn't just a suggestion or a guideline, it's woven into the very fabric of reality. According to Einstein's equations, as an object approaches the speed of light, its mass increases exponentially, requiring infinite energy to push it further. In other words, breaking this barrier isn't just difficult, it's fundamentally impossible under the laws of physics as we know them. But why is light speed so special? Think of it like this: light doesn't just move through space and time, it defines them. The speed of light is the thread that stitches together the universe, tying everything from gravity to causality into a cohesive whole. If something were to travel faster than light, it wouldn't just break a rule, it would unravel the very structure of reality, potentially leading to paradoxes like time travel or effects preceding their causes. It's no wonder scientists have spent decades grappling with this seemingly insurmountable barrier. Yet, for all its elegance, Einstein's theory leaves us with a tantalizing question. Is the light-speed barrier truly absolute, or are there ways to bend, stretch, or even circumvent it? This is where the boundaries of physics begin to blur, opening the door to extraordinary possibilities. Over the years, researchers have proposed a variety of creative solutions, some rooted in the quirks of quantum mechanics, others drawing from the strange geometry of spacetime itself. These ideas don't necessarily break the rules of relativity, but instead explore how we might work within or around them, and that's what makes this challenge so captivating. It's not just about defying a law of physics, it's about reimagining what's possible. So, as we dive deeper into these theories, keep this in mind: the speed of light isn't just a barrier, it's a beacon guiding us toward new frontiers of discovery. Whether we're talking about warp drives, wormholes, or quantum tunneling, each concept represents a bold step toward reshaping our understanding of the universe. And while the road ahead is filled with uncertainty, one thing is clear: the pursuit of faster-than-light travel isn't just about reaching distant stars, it's about challenging the very limits of human ingenuity. What if the key to faster-than-light travel isn't about moving through space, but bending space itself? Enter the Alcubierre warp drive, a concept that sounds like it's straight out of science fiction but is grounded in real physics. Proposed by physicist Miguel Alcubierre in 1994, this theory offers a way to bypass the cosmic speed limit set by Einstein's theory of relativity. Instead of trying to push a spacecraft to impossible speeds, the Alcubierre drive suggests manipulating the fabric of space-time. Imagine space as a stretchy sheet. The drive would contract space in front of the ship, pulling distant points closer while expanding space behind it, effectively creating a bubble that moves faster than light. The spacecraft itself wouldn't be breaking any physical laws, it would be riding this wave of warped space. But how does it work? The idea relies on something called negative energy, a hypothetical form of energy that could distort space-time in just the right way. Think of it as the opposite of gravity. Instead of pulling things together, negative energy would push space apart. To create the warp bubble, you'd need to generate an enormous amount of this energy, something far beyond our current technological capabilities. And that's not the only hurdle. The energy required is so immense that some estimates suggest it would be equivalent to the mass of a small planet. Even if we could generate that much energy, controlling it precisely enough to create a stable warp bubble is another challenge altogether. Then there's the question of what happens inside the bubble. Would the passengers experience time differently? Would they even feel like they're moving? Surprisingly, within the bubble, everything would feel normal. No crushing G-forces, no time dilation, just smooth sailing through the cosmos. It's a tantalizing idea, but one that's still firmly in the realm of theory. Scientists are actively exploring ways to make the Alcubierre drive a reality, from refining the math to searching for exotic materials that could generate negative energy. While it's a long shot, the very possibility keeps the dream of interstellar travel alive. After all, if we can bend space itself, the stars might not be as far away as they seem. Imagine a tunnel carved through the fabric of space and time, connecting two distant points in the universe, a shortcut that could bypass the vast emptiness between stars and galaxies. This isn't science fiction, it's the concept of a wormhole, one of the most intriguing ideas in theoretical physics. Wormholes, often depicted as cosmic shortcuts, are hypothetical structures that could, in theory, allow us to travel vast distances in the blink of an eye, or even traverse time itself. But how do they work, and could they ever be more than just a fascinating idea? At their core, wormholes are solutions to Einstein's equations of general relativity, which describe how gravity shapes the universe. Picture space-time as a flexible sheet. If you fold that sheet so that two distant points touch, a wormhole would act like a tunnel piercing through the fold, creating a direct path between them. This means that instead of traveling the long way around, you could take a shortcut through the wormhole, potentially arriving at your destination faster than light could travel through normal space. However, wormholes aren't as simple as they sound. For one, they require something called exotic matter to stay open and stable. Exotic matter isn't like the stuff we encounter in our everyday lives. It has negative energy density, which means it behaves in ways that defy our understanding of physics. This strange substance would be needed to counteract the natural tendency of a wormhole to collapse under its own gravity. The problem: exotic matter has never been observed in nature, and creating it in a lab remains far beyond our current capabilities. Even if we could find or create exotic matter, wormholes come with their own set of challenges and paradoxes. For example, traversable wormholes could potentially allow for time travel, raising questions about causality, the relationship between cause and effect. What happens if you travel back in time and change something? Could you create a paradox that unravels the very fabric of reality? These questions aren't just philosophical, they're deeply tied to the physics of wormholes and the laws that govern the universe. And then there's the issue of stability. Without exotic matter, wormholes would likely collapse almost instantly, making them useless for travel. Even with exotic matter, maintaining a stable wormhole would require precision and technology far beyond anything we can currently imagine. The slightest disturbance could cause the wormhole to collapse, trapping, or worse, destroying anything inside. Despite these challenges, wormholes remain a tantalizing possibility for faster-than-light travel. They represent a glimpse into the extraordinary potential of the universe, a reminder that the cosmos might hold secrets we've yet to uncover. While they may remain in the realm of theory for now, the study of wormholes pushes the boundaries of our understanding, challenging us to think bigger, bolder, and more creatively about the nature of space, time, and the universe itself. What if I told you there's a particle that doesn't just flirt with the speed of light but outright leaves it in the dust? Enter tachyons, a fascinating, if entirely hypothetical, concept in physics. These elusive particles are theorized to always travel faster than light, defying one of the most fundamental rules of our universe. While they've never been detected, the idea of tachyons has captured the imagination of scientists and science fiction writers alike, offering a tantalizing glimpse into what might be possible beyond the limits of light speed. Tachyons are unique not just because of their speed, but because of how they challenge our understanding of reality. According to theory, these particles don't just break the cosmic speed limit, they're born to do so. Unlike ordinary matter, which slows down as it approaches the speed of light, tachyons are thought to accelerate as they lose energy. The less energy they have, the faster they go. It's a bizarre twist that turns our everyday intuition upside down, and it's precisely this strangeness that makes them so intriguing. But what would it mean if tachyons were real? For starters, their existence could open up entirely new avenues for faster-than-light travel. If we could harness or interact with tachyons, we might find a way to send information, or even physical objects across vast distances almost instantaneously. Imagine a future where messages from Earth could reach distant star systems in mere moments, or where spacecraft could traverse the galaxy without being bound by the constraints of light speed. It's a thrilling possibility, but one that comes with its own set of mind-bending challenges. One of the most significant hurdles is the question of causality. If tachyons can travel faster than light, they could theoretically send signals backward in time, creating paradoxes that defy our understanding of cause and effect. For example, what happens if a tachyon message arrives before it's sent? These paradoxes aren't just theoretical puzzles. They could fundamentally alter how we perceive time and reality. Some physicists argue that the existence of tachyons would require us to rethink the very nature of time itself, potentially unlocking secrets about the universe that we can barely imagine. Of course, all of this remains firmly in the realm of speculation. Tachyons have never been observed, and many scientists remain skeptical about their existence. But even as a thought experiment, they push the boundaries of what we know and inspire us to ask deeper questions about the universe. Whether or not tachyons are real, their story is a reminder that the cosmos is full of mysteries waiting to be explored, and that sometimes the most extraordinary ideas are the ones that challenge us to think beyond the limits of the possible. One of the strangest and most intriguing phenomena in the universe is quantum entanglement, a concept so bizarre that even Albert Einstein famously called it spooky action at a distance. Imagine two particles separated by billions of light years, yet somehow intertwined in such a way that the state of one instantly influences the state of the other. It's as if they're connected by an invisible thread, bypassing the need for any physical signal to travel between them. This instantaneous connection defies our classical understanding of space and time, raising the tantalizing question: could we use this phenomenon to send messages or even travel faster than light? At its core, quantum entanglement occurs when particles become so deeply linked that they share a single quantum state. Measuring one particle immediately determines the state of its entangled partner, no matter how far apart they are. The implications are staggering. If we could somehow encode information into these entangled particles, we might be able to communicate across vast cosmic distances without waiting for signals to travel at the speed of light. It's a concept that sounds like science fiction, but it's rooted in real, experimentally verified physics. However, harnessing entanglement for practical applications is far from straightforward. While the connection between entangled particles is instantaneous, we can't actually control or manipulate the information they share in a way that would allow us to send deliberate messages. Think of it like having a pair of magical dice. No matter how far apart they are, rolling one die instantly determines the result of the other. But you can't choose what number appears, it's entirely random. This randomness is one of the biggest hurdles to using entanglement for faster-than-light communication. Another challenge lies in maintaining entanglement over long distances. Entangled particles are fragile. Any interaction with their environment can break the delicate link between them. Scientists have made progress in creating and preserving entangled particles in controlled laboratory settings, but scaling this up to interstellar distances is a monumental task. The technology required to protect and manipulate entangled states on such a scale doesn't yet exist, and it's unclear whether it ever will. Despite these obstacles, researchers haven't given up on the dream of leveraging entanglement for faster-than-light communication. Some theories suggest that while we may not be able to send messages faster than light, entanglement could still play a role in advanced propulsion systems or even in creating shortcuts through spacetime. For example, some speculative ideas propose using entangled particles to manipulate the fabric of spacetime itself, potentially opening the door to warp drives or wormholes. While these ideas remain firmly in the realm of theory, they highlight the incredible potential of quantum mechanics to reshape our understanding of the universe. Quantum entanglement reminds us that the cosmos is far stranger and more interconnected than we ever imagined. It challenges our notions of distance, time, and causality, offering a glimpse into the hidden rules that govern reality. While we're still far from turning this quantum weirdness into a practical tool for faster-than-light travel or communication, the possibilities are as vast and mysterious as the universe itself. And who knows, as our understanding of quantum mechanics deepens, we may one day find a way to harness this spooky action to explore the stars in ways we can barely imagine today. What if you could journey through space and time, returning home before you even left? This isn't just the stuff of science fiction, it's the tantalizing possibility presented by Krasnikov tubes. These theoretical pathways, first proposed by physicist Sergei Krasnikov in the 1990s, are like cosmic shortcuts that could allow faster-than-light travel by bending the fabric of spacetime itself. But here's where it gets mind-bending. These tubes aren't just about speed, they could also create closed time-like curves, a fancy way of saying they might let you travel back in time. Picture this: a spacecraft leaves Earth, enters a Krasnikov tube, and emerges back at its starting point before it even began its journey. Sounds impossible, right? Yet the math behind these tubes suggests it might be within the realm of theoretical physics. So how would a Krasnikov tube work? Imagine spacetime as a vast, stretchy fabric. Normally, traveling from one point to another means moving across this fabric at a speed limited by the laws of physics. But a Krasnikov tube would essentially create a tunnel through this fabric, compressing the distance between 2 points so drastically that a spacecraft could traverse it faster than light could travel through normal space. The catch: this tunnel would have to be pre-constructed by a civilization capable of manipulating spacetime on an unimaginable scale. And once created, it wouldn't just be a one-way trip, it could loop back on itself, creating a pathway that bends time. But with great power comes great paradoxes. The idea of traveling back in time raises all sorts of questions, like the infamous grandfather paradox. What if you went back and accidentally prevented your own existence? Krasnikov tubes don't just challenge our understanding of physics. They force us to confront the weird and wonderful implications of time travel. Could these paradoxes be resolved, or are they proof that such pathways are impossible? For now, Krasnikov tubes remain a fascinating thought experiment, a glimpse into what might be possible if we could master the very fabric of reality. And while we're far from building them, they remind us that the universe is far stranger and more exciting than we often realize. Black holes, those cosmic giants with gravity so intense that not even light can escape, might hold the key to one of the most daring ideas in faster-than-light travel, the black hole slingshot. Imagine a spacecraft approaching the edge of a black hole, skimming just close enough to be caught in its gravitational pull. The immense force could act like a cosmic slingshot, flinging the ship forward at speeds unimaginable with conventional propulsion. This isn't just science fiction, it's a concept grounded in the physics of gravity and momentum. The idea revolves around something called a gravity assist, a maneuver already used by spacecraft like Voyager and Cassini to gain speed by passing near planets. But with black holes, the scale is entirely different. The gravitational forces are so extreme that a properly calculated trajectory could theoretically propel a ship to a significant fraction of the speed of light. The energy required, it's already there, built into the black hole itself. It's like catching a ride on the universe's most powerful roller coaster. Of course, this comes with enormous risks. Getting too close to a black hole could mean crossing the event horizon, the point of no return where the gravitational pull is so strong that escape becomes impossible. Even a slight miscalculation could spell disaster. Radiation from the accretion disk, the swirling mass of gas and dust around the black hole, could also pose a deadly threat to any spacecraft. And then there's the challenge of navigation. Black holes warp space-time so severely that plotting a safe course would require precision beyond anything we've ever attempted. But let's say we could overcome these challenges. What could a black hole slingshot achieve? Some theories suggest that with the right conditions, a spacecraft could reach speeds close to the speed of light, drastically reducing travel time across the cosmos. It's a tantalizing possibility, one that could bring distant star systems within reach without the need for exotic warp drives or wormholes. The universe's most destructive forces might just become our greatest tool for exploration. The concept also raises fascinating questions about the nature of gravity and motion. Could we one day harness the power of black holes not just for speed, but for other applications in space travel? And what would it mean for our understanding of physics if we could manipulate such extreme forces? The black hole slingshot isn't just a shortcut through space, it's a gateway to rethinking how we interact with the cosmos. So, while the challenges are immense, the potential rewards are nothing short of revolutionary. Now, let's shift our focus to something truly mind-bending: the Casimir Effect. Picture this: even in the emptiest regions of space, where it seems like nothing exists, there's actually a hidden energy buzzing just beneath the surface. This energy, known as zero-point energy, is tied to the strange and unpredictable nature of quantum mechanics. And here's where it gets fascinating. The Casimir Effect gives us a glimpse into how this energy might be harnessed. At its core, the Casimir Effect occurs when two uncharged parallel metal plates are placed incredibly close together in a vacuum. Normally, you'd think nothing would happen, but quantum mechanics tells a different story. The vacuum isn't truly empty, it's teeming with virtual particles that pop in and out of existence. These particles create fluctuating electromagnetic fields, and when the plates are close enough, they suppress certain wavelengths of these fluctuations. The result, a tiny but measurable force pushing the plates together. This force is the Casimir Effect, and it's a direct manifestation of zero-point energy. So, could this energy be the key to faster-than-light travel? The idea is tantalizing. If we could somehow tap into zero-point energy on a larger scale, it might provide an almost limitless source of propulsion, one that doesn't rely on traditional fuel or massive amounts of energy. Some theorists have even speculated that manipulating zero-point energy could allow us to warp spacetime itself, creating a bubble that moves faster than light without breaking the laws of physics. But let's not get ahead of ourselves. While the concept is thrilling, the challenges are immense. Extracting usable energy from the quantum vacuum is no small feat. The Casimir Effect produces only minuscule forces, and scaling it up to something practical for space travel would require groundbreaking advancements in quantum engineering and materials science. Not to mention, we'd need to find a way to stabilize and control this energy without causing catastrophic side effects. Still, the potential is too exciting to ignore. The Casimir Effect reminds us that the universe is far stranger and more resourceful than we often assume. Who knows, one day this quantum quirk might just be the breakthrough that propels us to the stars. What if we could defy one of the most fundamental laws of physics, Newton's third law? That's exactly what the M-drive, or electromagnetic drive, claims to do. This controversial propulsion system has sparked heated debates in the scientific community, with some calling it revolutionary and others dismissing it as impossible. At its core, the M-drive proposes a way to generate thrust without expelling any propellant, essentially pushing against itself to create motion. Sounds like magic, right? Well, that's part of the reason it's so polarizing. The concept works by bouncing microwaves around inside a cone-shaped cavity, creating a difference in radiation pressure that supposedly produces thrust. No fuel, no exhaust, just electromagnetic waves doing the heavy lifting. Sounds simple, but here's the catch. It seems to violate the conservation of momentum, a cornerstone of physics. This is why many scientists remain skeptical, arguing that if the M-drive really worked, it would upend our understanding of the universe. Despite the skepticism, experiments have reportedly shown small amounts of thrust being generated, though the results are often inconsistent and difficult to replicate. NASA EagleWorks lab, for example, conducted tests that appeared to support the idea, but the findings were met with intense scrutiny. Critics argue that the observed thrust could be the result of experimental errors or external forces like thermal effects rather than a genuine breakthrough. Still, the allure of the M-drive is hard to ignore. If it could be proven to work, it would open up incredible possibilities for space travel. Imagine spacecraft that don't need to carry massive amounts of fuel, allowing them to travel farther and faster than ever before. Some even speculate that the M-drive could be a stepping stone toward faster-than-light travel, though that remains firmly in the realm of speculation for now. The debate over the M-drive is far from settled, but it serves as a fascinating reminder of how science pushes boundaries, challenges assumptions, and sometimes teeters on the edge of the impossible. Whether it's a groundbreaking discovery or a scientific dead end, the M-drive has already ignited imaginations and sparked conversations about what's truly possible in the cosmos. Now, let's shift our focus to a concept that feels like it's pulled straight out of science fiction: the Photon rocket. imagine harnessing the power of light itself to propel a spacecraft through the cosmos. The idea of a photon rocket revolves around using the momentum of light particles or photons to generate thrust. While it wouldn't break the light speed barrier, this technology could push us tantalizingly close to the ultimate speed limit of the universe. So how does it work? In simple terms, a photon rocket would emit a stream of photons, tiny packets of light, out the back of the spacecraft. According to the laws of physics, every action has an equal and opposite reaction. As those photons are expelled, their momentum would push the spacecraft forward. It's a bit like blowing up a balloon and letting it go, except instead of air, you're using light. The catch: light particles have an incredibly tiny amount of momentum, so generating enough thrust to move a spacecraft efficiently is a monumental challenge. One of the biggest hurdles is energy. To produce a meaningful amount of thrust, you'd need an enormous amount of energy to create and expel photons. Current technology isn't even close to making this practical. But let's say we could solve the energy problem. What would a photon rocket look like in action? It would likely be a sleek, lightweight vessel designed to maximize efficiency, with a propulsion system that could convert energy into light with minimal waste. Theoretically, such a ship could reach speeds approaching a significant fraction of the speed of light, making interstellar travel within a human lifetime a possibility. Of course, there are limitations. Even if we could build a photon rocket, it wouldn't achieve faster than light speeds. Light speed remains the universe's ultimate speed limit, and a photon rocket would be bound by that rule. Additionally, the immense energy requirements and the challenges of managing such a propulsion system make this concept a distant dream for now, but that doesn't mean it's not worth exploring. In fact, the photon rocket represents an important stepping stone in our quest to reach the stars. It pushes us to think creatively about how we can harness the fundamental forces of nature to explore the cosmos. So, where does the photon rocket fit into the bigger picture of interstellar travel? It's a reminder that sometimes the most groundbreaking ideas start small, literally, in this case with particles of light. While it may not be the solution to faster than light travel, it could play a crucial role in getting us closer to that goal. After all, every journey begins with a single step, or in this case, a single photon. What if the most destructive force in the universe could become the ultimate power source for interstellar travel? Enter the concept of the black hole engine, a theoretical propulsion system that taps into the raw energy of a singularity. Black holes, often seen as cosmic vacuum cleaners, are also unimaginably powerful energy factories. Their intense gravitational pull and the swirling accretion disks around them release staggering amounts of energy, some of which could, in theory, be harnessed by an advanced civilization. One of the most intriguing designs for a black hole engine revolves around what's called a Penrose process. Named after physicist Roger Penrose, this idea suggests that energy could be extracted from a rotating black hole by dropping matter into its ergosphere, a region just outside the event horizon where space itself is dragged around the black hole. If done precisely, this process could release energy equivalent to a significant portion of the matter's mass, potentially powering a starship for centuries. Imagine a spacecraft equipped with a miniature black hole, feeding it just enough matter to keep the engine running while avoiding the dangers of being swallowed whole. But the challenges here are as immense as the forces involved. First, creating or capturing a black hole small enough to be practical is far beyond our current technology. Then there's the issue of containment, keeping a black hole stable and preventing it from devouring the ship itself. And let's not forget the radiation and tidal forces, which would require shielding far beyond anything we've ever built. Still, the idea isn't entirely science fiction. Physicists like Stephen Hawking have suggested that microscopic black holes could exist, and if we could harness them, they might revolutionize how we think about energy and propulsion. The black hole engine represents both the promise and peril of faster-than-light travel. It's a reminder that the universe offers incredible opportunities, but unlocking them will require us to grapple with forces that push the limits of our understanding. So, while we're not building black hole-powered starships anytime soon, the concept challenges us to dream bigger and think beyond the boundaries of conventional physics. What if there's a cosmic exit door, a place where the universe itself spills out matter and energy rather than devouring it? Enter the white hole hypothesis, a fascinating, mind-bending concept that flips the script on everything we know about black holes. While black holes are cosmic vacuums pulling in everything that crosses their event horizon, white holes are theorized to be their exact opposites, cosmic fountains spewing out matter and energy into the universe. But could these mysterious phenomena be more than just theoretical curiosities? Could they, in fact, serve as gateways to other universes or even dimensions beyond our own? The idea of white holes emerges from the mathematics of general relativity, the same framework that predicts black holes. In theory, if a black hole is a one-way street where nothing can escape, a white hole is its reverse, a place where nothing can enter but everything can exit. Some scientists speculate that white holes might be connected to black holes through wormholes, creating a cosmic tunnel where matter and energy could travel vast distances or even exit our universe entirely. This raises the tantalizing possibility that white holes could be portals, not just to other regions of space, but to entirely different realities. Now, let's connect this to faster-than-light travel. If a white hole were to exist, and if it were linked to a black hole via a traversable wormhole, it could theoretically provide a shortcut through space-time. Instead of traveling across vast distances at sublight speeds, you could enter a black hole, traverse the wormhole, and emerge from a white hole in a completely different part of the universe, or even a different universe altogether. This would effectively allow for faster-than-light travel, not by moving through space, but by bending the very fabric of space-time itself. Of course, this is all highly speculative. White holes have never been observed, and their existence remains a topic of intense debate among physicists. Some argue that they might not even be stable enough to exist in the real universe, while others suggest they could be remnants of the Big Bang, cosmic echoes of the universe's birth. Regardless of their reality, the white hole hypothesis pushes the boundaries of our understanding and opens up thrilling possibilities for faster-than-light travel and interstellar exploration. So, while we may not have proof of white holes, yet the idea itself is a reminder of how much we still have to discover about the cosmos. It's a concept that challenges our imagination, inviting us to think beyond the limits of our universe and consider what might lie beyond. Could white holes be the key to unlocking the secrets of faster-than-light travel? Only time and perhaps a lot more math will tell. Quantum tunneling is one of those mind-bending phenomena that seems to defy the rules of classical physics. At its core, it allows particles to do something seemingly impossible, pass through barriers they shouldn't be able to cross. Picture a ball rolling up a hill. In the classical world, if the ball doesn't have enough energy to reach the top, it simply rolls back down. But in the quantum realm, that ball has a chance to suddenly appear on the other side of the hill, as if it teleported through it. This bizarre behavior is a cornerstone of quantum mechanics, and it's been experimentally proven time and time again. But here's the question: if particles can do this, could we scale it up to something much bigger? Like a spacecraft, could quantum tunneling be the key to breaking through the fabric of space-time and achieving faster-than-light travel? The idea hinges on the strange nature of quantum mechanics, where particles exist in a state of probability rather than certainty. They don't follow the straightforward paths we're used to in our everyday world. Instead, they can tunnel through energy barriers that, according to classical physics, should be insurmountable. This happens because particles also behave like waves, and these waves can extend into and even beyond barriers, allowing the particle to appear on the other side. It's as if the universe gives particles a tiny loophole to cheat the system. Now, imagine applying this principle to a spacecraft. Instead of a tiny particle, we're talking about an entire vessel traveling through space. The concept would involve creating a kind of quantum tunnel, a shortcut through the fabric of space-time itself. In theory, this could allow a ship to bypass the immense distances between stars by essentially tunneling through the barriers imposed by the speed of light. It's not about moving faster than light in the traditional sense, but rather finding a way to sidestep the problem altogether. But before we get too carried away, there are some massive hurdles to consider. Quantum tunneling works on an incredibly small scale, involving particles like electrons or photons. Scaling this up to the size of a spacecraft would require manipulating energies and forces on a level we can't even begin to comprehend with our current technology. The energy required to create a tunnel large enough for a ship would be astronomical, and we'd need to find a way to stabilize it without collapsing the entire structure. Plus, there's the question of how to control such a process. How do you ensure the ship ends up where you want it to go and not in some random corner of the universe? Despite these challenges, the idea of quantum tunneling for space travel is more than just science fiction. Some physicists have proposed that advanced civilizations might one day harness this phenomenon, using it to traverse the cosmos in ways we can only dream of today. While we're far from making this a reality, the concept reminds us that the universe is full of possibilities we've only just begun to explore, and who knows? Maybe one day, quantum tunneling will be the breakthrough that takes us to the stars. What if the key to unlocking faster than light travel has been all around us this whole time, hidden in plain sight? Dark matter, the invisible substance that makes up roughly 85% of the universe's mass, is one of the greatest mysteries in modern physics. We can't see it, touch it, or detect it directly, yet its gravitational effects shape the cosmos. But what if we could harness this enigmatic force? Could dark matter be the ultimate fuel for interstellar travel, propelling us beyond the limits of light speed? The idea of a dark matter drive is as intriguing as it is challenging. Unlike conventional fuels, dark matter doesn't interact with light or ordinary matter in any way we can easily observe. It's like trying to catch smoke with your bare hands. It's there, but it slips through your fingers. Scientists believe dark matter exists because of its gravitational influence on galaxies, but capturing and manipulating it is another story. If we could somehow collect and control it, the energy density of dark matter could theoretically dwarf anything we currently use for propulsion. Imagine a spacecraft powered by the very fabric of the universe itself. But the challenges are immense. First, we'd need to detect dark matter in a way that allows us to interact with it. Current experiments, like those using ultra-sensitive detectors deep underground, are designed to catch rare interactions between dark matter particles and ordinary matter. Even then, success has been elusive. If we ever do detect it, the next hurdle would be finding a way to store and channel its energy. Dark matter doesn't behave like conventional matter, so traditional engines or fuel tanks wouldn't work. We'd need to invent entirely new technologies, possibly leveraging exotic physics we haven't even discovered yet. Despite these obstacles, the potential rewards are staggering. A dark matter drive could provide a virtually limitless source of energy, enabling spacecraft to accelerate to incredible speeds without the need for massive fuel reserves. It could open the door to journeys that take us to distant stars and maybe even beyond our galaxy. Plus, because dark matter is so abundant, we wouldn't have to worry about running out of fuel. The universe itself would be our gas station. Of course, this is all speculative for now. Dark matter remains one of the biggest unsolved puzzles in science, and turning it into a propulsion system is a leap into the unknown. But history has shown us that the greatest breakthroughs often come from tackling the impossible. Who knows, the invisible force that holds galaxies together might one day carry us to the stars. And that's a thought worth exploring. What if the key to unlocking faster than light travel lies in one of the most elusive and powerful substances in the universe, antimatter? This extraordinary material is the ultimate energy source, packing more punch per gram than anything else we've ever discovered. When antimatter meets matter, it annihilates in a flash of pure energy, releasing a staggering amount of power. To put it in perspective, just 1 gram of antimatter could produce an explosion equivalent to 43,000 tons of TNT. That's the kind of energy that could propel a spacecraft to near-light speeds, making interstellar travel a tangible possibility. But how exactly could antimatter power a rocket? The idea is both simple and mind-bending. A spacecraft equipped with an antimatter propulsion system would store small amounts of antimatter, carefully isolated from matter to prevent premature annihilation. When needed, controlled amounts of antimatter would be allowed to interact with matter, creating bursts of energy that could be directed to produce thrust. Unlike traditional rockets, which rely on chemical reactions, an antimatter engine could achieve speeds that bring us closer to the dream of reaching distant stars within a human lifetime. Of course, the challenges are as enormous as the potential. Producing antimatter is no small feat. Currently, we can only create tiny quantities in particle accelerators, and even then, its incredibly expensive estimates suggest producing 1 gram of antimatter could cost trillions of dollars. Storing it is another hurdle. Antimatter must be kept in a vacuum and suspended by powerful magnetic fields to prevent contact with matter. One slip up and the entire system could self-destruct. These obstacles make antimatter propulsion a tantalizing but daunting prospect. Yet, despite these hurdles, the promise of antimatter rockets keeps scientists and engineers pushing forward. Imagine a future where we've mastered the production and storage of antimatter, where spacecraft equipped with these engines could zip across the cosmos, reaching destinations that once seemed impossibly distant. It's a vision that blends cutting-edge physics with the timeless human drive to explore the unknown. And while we're not there yet, the pursuit of antimatter propulsion reminds us that sometimes the most extraordinary journeys begin with the tiniest particles. Imagine a spacecraft that doesn't rely on traditional fuel or engines, but instead is propelled forward by the sheer power of light. This is the essence of the laser sail concept, a futuristic idea that could revolutionize how we think about interstellar travel. At its core, a laser sail spacecraft would use an enormous, highly reflective sail like a giant mirror to catch and harness the momentum of powerful laser beams. These beams, fired from a ground-based or orbital laser array, would push the sail to speeds previously unimaginable, potentially enabling journeys to distant stars within a human lifetime. The beauty of this idea lies in its simplicity. Light, though it has no mass, carries momentum. When photons from a laser strike the reflective sail, they transfer that momentum, gently but persistently pushing the spacecraft forward. Over time, this continuous push could accelerate the craft to a significant fraction of the speed of light. Unlike chemical rockets, which burn through their fuel quickly, a laser sail could theoretically keep accelerating as long as the laser keeps firing. This makes it an incredibly efficient system for long-distance travel, but let's not gloss over the challenges. Building a laser powerful enough to propel a spacecraft across interstellar distances is no small feat. We're talking about lasers that would require energy outputs on the scale of entire nations. And then there's the sail itself. It would need to be incredibly lightweight yet durable enough to withstand the intense laser beams and the harsh conditions of space. Even the slightest imperfection in the sail's surface could scatter the laser light, reducing efficiency and potentially derailing the mission. Another hurdle is precision. The laser would need to stay perfectly focused on the sail, even as the spacecraft moves farther and farther away. At interstellar distances, even the tiniest misalignment could cause the laser to miss its target entirely. This would require advanced tracking systems and possibly even a network of relay stations to keep the beam on course. Despite these challenges, the potential rewards are staggering. A laser sail could make travel to nearby star systems like Proxima Centauri, a realistic goal within decades rather than millennia, and because the laser system remains in our solar system, the spacecraft itself doesn't need to carry fuel, making it lighter and faster. This opens up exciting possibilities for sending probes, or even small crewed missions, to explore the cosmos like never before. So, while the laser sail concept is still in its infancy, it represents a bold step toward breaking the boundaries of space travel. It's a reminder that sometimes the most revolutionary ideas come from looking at the universe in a completely new way, like riding beams of light to the stars. What if the key to faster-than-light travel isn't about moving through space at all, but about manipulating time itself? This is where the mind-bending concept of time dilation comes into play. According to Einstein's theory of relativity, time doesn't tick at the same rate for everyone. If you're traveling close to the speed of light, time slows down for you relative to someone standing still. From the perspective of an outside observer, it might look like you've traveled faster than light, even though, from your perspective, you haven't broken any cosmic speed limits. This is the foundation of the time warp idea, a way to effectively cheat the system by bending the rules of time. But how does this work in practice? Imagine you're on a spaceship traveling at an incredible speed, close to the speed of light. For every year that passes for you on that ship, decades or even centuries could pass for someone back on Earth. This means that, from Earth's perspective, you've covered vast distances in what feels like no time at all. It's not that you've moved faster than light. It's that time itself has warped around you, creating the illusion of superluminal travel. This phenomenon isn't just science fiction. It's been experimentally verified with atomic clocks on fast-moving airplanes, though the effects are minuscule at those speeds. Now, let's take this a step further. What if we could amplify this effect, creating a deliberate time warp? Some theories suggest that powerful gravitational fields, like those near black holes, could act as natural time machines, slowing time dramatically for anyone who ventures close. If we could harness or replicate such extreme conditions, we might be able to create a controlled time warp, effectively allowing us to traverse the cosmos in what feels like an instant, at least from the outside. But here's the catch. While this might solve the problem of speed, it introduces a host of paradoxes and challenges. For example, if you arrive at your destination centuries after you left, what happens to the people and places you left behind? Are you traveling through time as much as you're traveling through space? And then there's the question of causality. Time dilation doesn't just mess with clocks, it messes with cause and effect. If you could manipulate time to this degree, could you create scenarios where effects precede causes, or where events become untethered from their natural order? These aren't just philosophical musings, they're real hurdles that any practical application of time warps would need to address. The idea of faster-than-light travel through time manipulation is as thrilling as it is fraught with complications. It challenges our understanding of the universe, pushing the boundaries of what we think is possible, and reminding us that, when it comes to the cosmos, the rules are anything but simple. What if the key to faster-than-light travel lies not in our three-dimensional world, but in dimensions we can't even see? This is the intriguing premise behind the hyperspace hypothesis, a concept that suggests the universe might be far more complex than it appears. According to this theory, hidden higher dimensions could exist, folded and twisted in ways that create shortcuts through space, shortcuts that might allow us to traverse vast cosmic distances in the blink of an eye. At the heart of this idea is string theory, a framework in physics that attempts to reconcile the laws of quantum mechanics with gravity. String theory proposes that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. And for these strings to make sense mathematically, they require the existence of extra dimensions, up to 10 or even 11 in some versions of the theory. These hidden dimensions could be compacted, curled up so tightly that we don't notice them in our everyday lives, but they might hold the key to unlocking hyperspace travel. So how would hyperspace travel work in practice? Imagine our universe as a flat sheet of paper. To get from one side to the other, you'd normally have to travel across the entire surface. But what if you could fold that paper, bringing two distant points together? In this analogy, hyperspace would be like poking a hole through the folded paper, creating a shortcut. By accessing these higher dimensions, a spacecraft could theoretically bypass the vast distances of our three-dimensional universe, enabling faster-than-light travel without breaking Einstein's speed limit. But here's the catch: accessing hyperspace isn't as simple as flipping a switch. For one, we have no idea how to detect or interact with these extra dimensions, let alone manipulate them. Even if they exist, they might be so small or so tightly wound that they're effectively out of reach. And then there's the energy problem. Opening a doorway to hyperspace would likely require unimaginable amounts of energy, far beyond anything we're capable of producing today. Still, the idea of hyperspace travel is more than just science fiction. It's a tantalizing possibility that challenges our understanding of the universe and pushes the boundaries of what we think is possible. While the challenges are immense, the potential rewards shortcutting across the cosmos, exploring distant stars, and even unlocking the secrets of the universe itself are equally profound. So, as we continue to probe the mysteries of string theory and higher dimensions, who knows, the path to faster-than-light travel might just be hiding in plain sight, or rather, in dimensions we can't yet see. What if the key to faster-than-light travel lies not in pushing against something, but in pushing against nothing? This is the fascinating idea behind the quantum vacuum thruster, a concept that sounds like it's straight out of science fiction but is rooted in real scientific principles. Let's break it down. At its core, the quantum vacuum thruster relies on the idea that space isn't truly empty, it's teeming with energy. Even in the void of space, particles and antiparticles constantly pop in and out of existence, a phenomenon known as quantum fluctuations. These fleeting bursts of energy are part of what physicists call the quantum vacuum. The quantum vacuum thruster proposes that by manipulating this energy, we could create thrust without needing any traditional fuel or propellant. Instead of pushing against matter, the thruster would essentially push against the fabric of space itself. The most famous example of this concept is the controversial M-Drive, a device that claimed to generate thrust by bouncing microwaves within a closed chamber. While initial tests seemed to show small amounts of thrust, the results were widely debated, with many scientists questioning whether the effect was real or just an experimental error. The big problem: the M-Drive appeared to violate the law of conservation of momentum, a fundamental principle of physics. If it works, it would mean we've discovered a way to create motion without expelling mass, a game changer for space travel. But here's the catch: pushing against the quantum vacuum isn't as simple as it sounds. The quantum vacuum isn't a physical object, it's a sea of energy that doesn't behave like anything we're familiar with. Some physicists argue that interacting with it to produce thrust is impossible, while others believe it's just a matter of figuring out the right approach. The debate is far from settled, and experiments continue to explore the potential of this technology. If a quantum vacuum thruster could be perfected, the implications for faster-than-light travel are staggering. Without the need for massive fuel supplies, spacecraft could theoretically achieve incredible speeds, potentially opening the door to interstellar exploration. But for now, the concept remains on the edge of science and speculation, a tantalizing idea that challenges our understanding of physics and the universe. So, is the quantum vacuum thruster a glimpse of the future or a scientific dead end? Only time and more research will tell. Now, let's take things to an even grander scale. What if we could harness the power of an entire star to propel ourselves through the cosmos? Enter the concept of a stellar engine, a megastructure so vast and ambitious that it could move not just a spaceship but an entire star system. Imagine the possibilities: a civilization with the ability to reposition their sun, and by extension, every planet orbiting it across the galaxy. But could such a colossal feat of engineering unlock the secrets of faster-than-light travel? Stellar engines come in different designs, but one of the most intriguing is the Alcubierre thruster. Picture this, a massive reflective structure like a mirror the size of a continent positioned near a star. By reflecting a portion of the star's light and radiation, this mirror creates a gentle but constant thrust, nudging the star and its planetary system in a specific direction over millions of years. While this might sound like science fiction, the physics behind it is surprisingly sound. The challenge, of course, lies in the sheer scale of such a project. Building and maintaining a structure of this magnitude would require resources and technology far beyond our current capabilities. But here's where it gets even more fascinating. Some theorists suggest that advanced civilizations might use stellar engines not just for slow, steady movement, but as part of a broader strategy for faster-than-light travel. For example, by repositioning a star system closer to a wormhole or a cosmic shortcut, they could reduce the time needed to traverse vast distances. Alternatively, a stellar engine could be used to accelerate a star to relativistic speeds, effectively turning the entire system into a kind of interstellar arc. The idea is mind-boggling, but it raises questions about the limits of engineering and the ingenuity of civilizations far more advanced than our own. Of course, the challenges are immense. Beyond the technical hurdles of constructing a stellar engine, there's the question of stability. Moving a star could disrupt the delicate gravitational balance of its planetary system, potentially endangering any life forms inhabiting it. And then there's the energy cost. Such a project would require unimaginable amounts of power, likely on a scale we can barely comprehend. Yet, the concept of a stellar engine forces us to think big. It challenges us to imagine what might be possible if humanity or another species could master the forces of an entire star. While faster-than-light travel might not be the immediate goal, the idea of moving stars themselves opens up a universe of possibilities, pushing the boundaries of what we consider achievable. And who knows, perhaps one day in the distant future, our descendants might look up at the night sky and see not just stars, but the engines that carry them across the cosmos. Imagine surfing on the fabric of the universe itself. Gravitational waves, those ripples in space-time caused by cataclysmic events like colliding black holes or merging neutron stars, have fascinated scientists since their detection in 2015. But what if these cosmic tremors could do more than just reveal the secrets of the cosmos? What if they could propel us across the stars, enter the gravitational wave drive, a concept that suggests we might one day ride these ripples to achieve faster-than-light travel? Gravitational waves are like the echoes of the universe's most violent events, carrying energy across vast distances. Unlike light, which can be blocked or absorbed, these waves pass through almost everything, making them a tantalizing prospect for propulsion. The idea here is to harness the energy of these waves, essentially using them as a kind of cosmic surfboard to push a spacecraft forward. But how would that even work? One proposed method involves creating a device capable of detecting and amplifying gravitational waves. Think of it as a gravitational wave sail, similar to how solar sails use the pressure of light from the sun to move through space. Instead of light, this sail would catch the energy of passing gravitational waves, allowing the spacecraft to gain momentum without traditional fuel. The challenge, of course, is that gravitational waves are incredibly faint by the time they reach us, so we'd need a way to either amplify them or generate our own, a feat that's far beyond our current technology. Another angle explores the possibility of generating artificial gravitational waves. If we could create controlled ripples in space-time, we might be able to manipulate them to create a kind of wave that a spacecraft could ride. This would require an immense amount of energy and a deep understanding of how space-time behaves under extreme conditions. While it sounds like science fiction, The principles are grounded in Einstein's theory of general relativity, which describes how massive objects warp space-time. The appeal of this idea lies in its elegance. Unlike other faster-than-light concepts that rely on exotic matter or bending the laws of physics, a gravitational wave drive works within the framework of what we already know about the universe. It's a reminder that sometimes the most groundbreaking solutions are hidden in the natural phenomena around us. But let's not get ahead of ourselves. There are still enormous hurdles to overcome, from the energy requirements to the engineering challenges of building such a device. What's fascinating is that this concept bridges the gap between theoretical physics and practical exploration. It's not just about understanding the universe, it's about finding ways to navigate it. And while we're still far from turning this idea into reality, the very possibility opens up a world of questions. Could we one day surf the ripples of space-time to reach distant stars? Only time and a lot of scientific ingenuity will tell. Now, let's dive into one of the most fascinating ideas in faster-than-light travel, the plasma bubble. Picture a spacecraft surrounded by a shimmering, glowing shield of plasma, a superheated, ionized gas that not only protects it from the dangers of space but also propels it forward at mind-bending speeds. This isn't just science fiction, it's a real concept being explored by scientists and engineers, and it could revolutionize how we think about interstellar travel. The idea behind the plasma bubble is to create a protective cocoon around a spacecraft, shielding it from cosmic radiation, micrometeoroids, and other hazards that lurk in the void of space. But it doesn't stop there. This bubble could also act as a propulsion system, using the energy of the plasma to push the spacecraft forward at speeds that approach or even surpass the speed of light. Imagine surfing through space on a wave of plasma, harnessing one of the most energetic states of matter to break the cosmic speed limit. So, how would this work? Plasma propulsion systems already exist in smaller forms, like ion drives, which use electric fields to accelerate ions and generate thrust. But a plasma bubble takes this concept to a whole new level. By creating a sustained, stable bubble of plasma around a spacecraft, we could potentially reduce the drag caused by interstellar particles and even manipulate the fabric of spacetime itself. Some theories suggest that a plasma bubble could interact with the quantum vacuum, effectively creating a warp-like effect that allows the spacecraft to move faster than light without violating the laws of physics. Of course, the challenges are immense. Creating and maintaining a plasma bubble large enough to envelop a spacecraft would require enormous amounts of energy, far beyond what we can currently generate. Stabilizing the plasma to prevent it from collapsing or becoming unstable is another hurdle. And then there's the question of how to control such a system. How do you steer a spacecraft when it's encased in a bubble of superheated gas? Despite these challenges, the potential is undeniable. A plasma bubble could protect astronauts from the harsh environment of space while propelling them to distant stars in a fraction of the time it would take with conventional methods. It's a concept that combines cutting-edge physics with the dream of exploring the cosmos, and it's a reminder that the boundaries of what's possible are constantly being pushed. Who knows, one day surfing through space on a plasma bubble might not just be a theory, it could be the key to unlocking the stars. Now, let's dive into the mind-bending world of quantum mechanics, where the rules of reality as we know them seem to bend and twist. Imagine a particle that isn't just here or there but exists in multiple places at once. This isn't science fiction, it's quantum superposition, a fundamental principle of quantum physics. But what if we could harness this phenomenon to achieve something even more extraordinary: instantaneous travel? It's a tantalizing idea, one that blurs the line between science and speculation. At the heart of this concept is the idea that particles, like electrons, can exist in multiple states simultaneously until they're observed. Think of it like a cosmic game of hide and seek, where the particle is hiding in all possible locations at once. Now extrapolate that to a human traveler. Could we, in theory, place ourselves in a state of superposition, existing in multiple places at the same time, and then collapse that state to appear instantly at our destination? It's a wild thought, but one that has sparked serious discussions among physicists and science fiction writers alike. The challenge, of course, is scale. Quantum superposition works beautifully for tiny particles, but scaling it up to something as complex as a human being introduces a universe of complications. For one, maintaining coherence, keeping all those quantum states intact, is incredibly difficult. Any interaction with the environment, even a stray photon, could collapse the superposition, ruining the effect. It's like trying to balance a house of cards in a windstorm. And even if we could overcome that hurdle, there's the question of how to control where and when the traveler reappears. Without precise manipulation, the quantum leap could end up being more of a quantum gamble. Despite these challenges, the idea of quantum superposition as a gateway to faster-than-light travel remains a fascinating area of exploration. Some theories suggest that entangled particles that remain connected regardless of distance, could provide a pathway for instantaneous communication or even transportation. If we could entangle a traveler with a destination, could we effectively teleport them across vast distances? It's a concept that pushes the boundaries of our understanding of physics and raises as many questions as it does possibilities. While the practical applications of quantum superposition for travel remain firmly in the realm of speculation, the concept serves as a reminder of just how strange and wondrous the universe can be. It challenges us to think beyond the limits of classical physics and imagine a future where the rules of space and time are no longer constraints but tools to be mastered. Whether or not quantum superposition ever becomes a viable means of travel, it's a testament to the power of human curiosity and our relentless drive to explore the unknown. What if the vastness of our universe isn't the end of the story? What if there are countless other universes, each with its own unique laws of physics, stars, and perhaps even civilizations? This is the tantalizing idea behind the multiverse, a concept that has fascinated scientists and storytellers alike. But here's the twist: if these parallel universes exist, could faster-than-light travel be the key to unlocking the door between them? The idea of multiverse travel hinges on some of the most mind-bending theories in physics. One of the leading candidates is the concept of wormholes, hypothetical tunnels through space-time that could connect distant points or even different universes. While wormholes are often discussed in the context of our own universe, some theories suggest they could extend beyond, acting as bridges to other realities. But here's the catch: traversing a wormhole would require faster-than-light travel, or at least a way to manipulate space-time on an unimaginable scale. Another intriguing possibility comes from string theory, which proposes that our universe might be just one brain floating in a higher dimensional space. If that's true, it's possible that other universes exist alongside ours, separated by dimensions we can't perceive. Faster-than-light travel, or something even more exotic, might be the only way to jump between these brains. It's a wild idea, but it raises a fascinating question. If we could find a way to move between universes, what would we discover? Would we encounter versions of ourselves living out different lives, or entirely alien realities governed by physics we can't even comprehend? Of course, this is all speculative, borderline science fiction, but that's part of what makes it so exciting. The connection between faster-than-light travel and multiverse exploration pushes the boundaries of what we think is possible. It challenges us to rethink not just how we move through space, but what space and reality itself might truly be. So, while we're still far from building a multiverse gateway, the theories behind it remind us just how much we have yet to explore. Whether or not we ever find a way to travel between universes, the pursuit of these ideas keeps our curiosity alive, driving us to uncover the deepest mysteries of existence. And who knows, maybe one day the stars won't be the only destination we dream of reaching. As we marvel at the incredible theories surrounding faster-than-light travel, it's impossible to ignore the immense challenges standing between us and this groundbreaking achievement. The dream of zipping across the cosmos at speeds beyond light's reach isn't just a matter of building faster engines or unlocking new energy sources. It's a puzzle that touches every corner of science, ethics, and even philosophy. Take, for instance, the technological hurdles. Even if we could harness the energy required to warp space or create a stable wormhole, the materials and precision needed are far beyond our current capabilities. Imagine trying to construct a spacecraft that can withstand the mind-bending forces of a warp bubble or a wormhole's gravitational extremes. These aren't just engineering challenges, they're barriers that push the limits of our understanding of physics itself. And let's not forget the energy requirements. To bend space-time or propel a ship faster than light, we'd need amounts of energy that dwarf anything humanity has ever produced. Some estimates suggest we'd need the equivalent of the entire energy output of a star just to make a single trip, but the challenges don't stop at technology. There's also the ethical dimension to consider. If we ever achieve faster-than-light travel, who gets to benefit from it? Will it become a privilege for the wealthy, or will it be accessible to all? And what about the impact on distant civilizations we might encounter? The potential for cultural disruption, exploitation, or even conflict is a sobering reminder that progress comes with responsibility. Then there's the philosophical side of the equation. Faster-than-light travel doesn't just change how we move through the universe, it challenges our understanding of time, causality, and our place in the cosmos. If we can outrun light, we're essentially rewriting the rules of reality as we know it. What does that mean for concepts like cause and effect or even free will? These questions might sound abstract, but they're deeply tied to the very fabric of our existence. Despite these challenges, the rewards of achieving faster-than-light travel are nothing short of transformative. Imagine a future where humanity isn't confined to a single star system, where we can explore distant galaxies, meet alien civilizations, and unlock the secrets of the universe. It's not just about the thrill of discovery, it's about survival. With faster-than-light travel, we could escape existential threats like supernova or asteroid impacts, ensuring the long-term survival of our species. So, while the road ahead is daunting, it's also filled with promise. The challenges we face aren't just obstacles, they're opportunities to push the boundaries of what's possible, to rethink our place in the universe, and to create a future that's as bold as the stars themselves. And who knows, with enough ingenuity, determination, and a bit of cosmic luck, we might just find a way to break the ultimate speed limit. Faster-than-light travel isn't just a scientific challenge, it's a testament to humanity's boundless curiosity and desire to explore. From the mind-bending possibilities of warp bubbles to the cosmic shortcuts offered by wormholes, every theory we've explored today paints a picture of a future where the universe is no longer out of reach. These ideas, while still speculative, remind us that the limits of what we can achieve are constantly shifting. They challenge us to think bigger, to dream bolder, and to keep asking the questions that drive progress. As we stand on the edge of what we know, it's worth reflecting on how far we've come. Just a century ago, the idea of traveling to the moon was science fiction. Today, it's history. Who's to say what the next 100 years will bring? The stars may seem distant now, but every breakthrough, every experiment, every bold new theory brings us one step closer to turning science fiction into science fact. Thank you for exploring these 25 incredible theories with us. Whether you're a seasoned space enthusiast or just starting to ponder the mysteries of the cosmos, we hope this journey has sparked your imagination. If you enjoyed this video, don't forget to hit the like button, subscribe for more deep dives into the universe's greatest mysteries, and share your thoughts in the comments below. What theory excites you the most? What do you think the future of space travel holds? Let's keep the conversation going. Until next time, keep looking up because the stars are waiting.